responsible, largely responsible for the bulk of the support of this project, was just couldn't nail him down. He's really busy. So we're going to record it. So he requested that, and we'll send that to him. And Dan and Craig too, if they can't join. Thank you, Molly.
Sure.
So I'll kick it off here with just a brief introduction. Well, I'm not sure everybody knows. Does everybody know each other? Well, no, Jeremy doesn't know everybody. So I'm going to I'll introduce myself first, and I'll hand it off to somebody, and then let's keep handing it off till we get everybody. I am Jeff Skelding, Director of Friends of the Upper Delaware River. I'll hand it off to Molly.
Hi, everyone. Molly, Policy Director at Friends of the Upper Delaware River, and I'll hand it off to Walter.
Yeah, I'm just a fly fisherman.
Yeah, and
I'll hand it to Joe.
Hi, I'm Joe Spancher. I'm one of the friends in Friends of the Upper Delaware. Glenn?
And a board member.
And a board member.
I'm Glenn. I'm also a fly fisherman, and I live on the river.
Good.
And you're handing it off to Ben, right, Glenn?
That's a good idea. How about that, Ben? Ben, you got to turn your volume on.
You're on mute, Ben.
He's on mute. There you go.
Okay. Hey, thank you very much, Glenn. Good to see everybody. I'm Ben Rinker, East Branch Outfitters, and I don't know who to hand it off to.
You can hand it off to the only one left is Jeremy.
Oh, there you go, Jeremy.
Yeah, thank you. My name is Jeremy Dietrich. I'm an aquatic ecologist at Cornell University. Been doing various ecological and aquatic restoration projects there for a little over 20 years now. So yeah, happy to look forward to going through some of the results that I have compiled here with associated with this project.
Jeremy, I'll just add that the four angling guys on this call have dozens and dozens of years of accumulated experience on the entire tailwater system. So just so you know, have some more context there. And I think 3 of them are homeowners right on the river. Unless, Walter, you got a house up here I'm unaware of.
No, I live at the Colonial when I'm up fishing.
Right, right. All right, so most of you know, and some of you have supported the invigoration of a macroinvertebrate study. All of you are aware of the questions about bugs on the river that are hovering around us at all times. And it's kind of difficult, it's been difficult for anybody to really sink their teeth into any kind of substantive way about the bug population on the river. Most of the information we have is anecdotal. There is some historical data, and that was phase 1 of this project, which Jeremy will talk about. And then, which was, I think, just a desktop, I think could be correctly characterized as a desktop exercise in finding out what is out there in the world of bugs for the Upper Delaware from any agency or organization. That was phase 1. We did it, and then entered into the field part of it, phase 2, which some of you helped with, whether you know it or not. Glenn, you and Dan donated your land for Jeremy to get on, and I'm kidding, Glenn, I know you did, and Jeremy did that, and is sort of, I think, halfway through that, Jeremy, maybe, or you can tell us, but for me, it's to receive, during the fishing season especially, weekly visits through the front door, people saying, what happened to this bug, what happened to that bug, we're concerned. There seems to be, I remember when, right? So the best I could think about was, I felt like FUDR was, if it would be important for the organization to attempt to sort of begin to look at that in the absence of anything else. So that's what got this all started. I approached some of you to help. You did. Thank you very much. And we found Jeremy. So with that, Jeremy, do you need to screen share? Molly, Jeremy?
It looks like I have
Yeah, you should be able to.
Okay, thank you. If you want to jump into it, Jeremy, go for it.
Yep.
Glenn, do you have a hard stop at some point?
Yeah, well, yeah, it's let's see, it's 2 hours from now.
Oh, okay, well, that should be fun.
Yeah, I think there's maybe about 25 slides. Let's see, so, all right, looks like that's up on mine. Is everything good on the receiving end there? You can see the
Yeah, I
presentation.
can see it.
Yeah.
Jeremy, how do you want to do it? You want people just to jump in whenever they have questions, or would that work for you, or do you want to?
I would say if you have a broader question, maybe just wait, just because I might actually be answering it like 2 slides later. But if you have like an interpretation question on like a graph and what does this point mean, or what do these lines mean, then
Okay,
feel free to jump in so that you so that you understand what you're seeing. So yeah, kind of calling this like 2023 interim report with respect to some of the field work and kind of a phase 2 approach that we've conducted this season, that, as Jeff indicated, was organized and launched by the Friends of the Upper Delaware River. And of course, I acknowledge, to thank Jeff and the organization for, kind of getting this off the ground, and the private funders who, have made this work possible. So a kind of a brief presentation outline. I'm going to do a quick recap on kind of the phase 1 results and recommendations, which kind of segued into where we are now. The general phase 2 kind of planning, organization, some sample site selection, then go into the in-stream habitat, substrate, methods and results, macro sampling methods, and family level abundance results. Look at some taxonomic richness outcomes, and then trying to superimpose that on some of the water temperature, kind of a water temperature investigation, pulling some of the USGS gauge data, looking at the correlations we have with that, and kind of a summary into the remainder of kind of this phase 2 kind of through early 2024 to kind of close it out, at least what our original plan was. So I think some of you were on the phase 1 kind of broader and presentation and summary. I think it was maybe 2 years ago now, or 18 months ago, where when I was approached, kind of there were 2 or 3 very broad overarching questions, as Jeff alluded to, that were of concern, to folks in the Upper Delaware. What is the existing state of the macro populations in that subbasin? Do we see any evidence of a macro population shifted over time? As Jeff indicated, a lot of statements and analogies of how things used to be, and with discussion of the reservoir release regimes and changing of the release regimes, do we see any evidence that such regimes are influencing the macro populations? So from that phase 1, we identified that yes, there is existing macro data, largely from state agencies and federal system. The DEC has kind of a widespread biomonitoring program, and they sample in the Upper Delaware through their rotating integrative basin studies. About every 5 years or 6 years, they return to the larger basins in the state. The PA, Department of Environmental Protection, has sampling sites, but mostly on the main stem, lower on the river system. And then there's been a few studies associated with the national park reach as well. However, what we discovered is that being able to articulate conclusions, sound statistical conclusions of some of this prior data is challenging because, either there was no replication, somebody would go somewhere once and that's it. And, intermittent time series collections. For instance, with some of the DEC data, we'd get a sample at, I don't know, Downsville, if it was, 1987 and 2006, I mean, it's kind of hard to, draw any conclusions in those, of course, they were just single collections. We didn't have a range. We couldn't calculate, standard deviations to be able to compare across sites. So, from that, we determined that, there's a phase 2 field collection effort would aid in, assessing these Upper Delaware conservation needs and, what, if any, New York DEP reservoir release regime effects may be present. So it leads us to now or this year. So for our phase 2, decided on a 2023 summer field effort. In cooperation with Jeff and I suppose indirectly some of you, we selected sites along longitudinal gradients, which is basically just kind of a run-of-river gradient. If you're not familiar with the term, on the West Branch, East Branch, Lower Beaver Kill, and on the Delaware River main stem. And each of these, so just for kind of general, wording vernacular. So a sample site is, where you're going kind of to collect it. And then at each of these sites, there's going to be 3 replicates per site. So, if I mention site categorically, it's like a broader geographical location. And then, replicates are, individual samples within that site, if that makes sense. So we collected 3 sample replicates per site to provide that needed increased statistical power and enable the capacity for some historical trend analyses. We went and collected in mid-July, kind of during the height of the annual growing season, kind of try to optimize the what productivity exists in the system. Normally I would do the substrate and the invertebrate collections kind of simultaneously, but given the the high water and all the rain this year, we had pretty narrow windows to collect, so I didn't want to dawdle too much while I was collecting the invertebrates. I just wanted to make sure we got that done, and so I had to return in early September when some of the higher water levels kind of subsided to go back and document the in-stream habitat or substrate composition component. And then the macro samples are being processed, picked, sorted, ID'd. I have half of those done now, which is what this report will be, and then I'll continue kind of a second subset the next few months, and there'll be a broader comprehensive report similar to what the phase 2, or I'm sorry, the phase 1 report was out later this spring prior to that can help inform any potential future work. So with 12 sites spread out throughout the Upper Delaware Basin, 5 sites on the West Branch, 3 sites on the Upper East, I think, as you guys call it, kind of above the junction, 1 site on the Lower Beaver Kill, and then 3 sites kind of along the main stem section of the river. So the first thing we want to know is, or what would be useful is what type of habitat do we have in these systems? And so, the invertebrates obviously need, quality habitat to persist and, optimize their populations. So, we went out, and these are very kind of standardized stream ecology related techniques. So at each site, remember, we have 3 replicates. At each replicate, we ran a tape out, excuse me, 50 feet from the bank. And then using what's called a blind touch random particle encounter. It's also kind of called the Woolman pebble count method, if you're familiar with that, those things. And that's basically every 6 inches along the tape, you're standing there, here's, a particular, whatever, 18 inches, you take your finger and you just kind of blindly, avert your eyes, you just blindly touch down, onto the bottom of the river, and the type of substrate or particle that you encounter is what you record. So, it's called a blind touch because you don't want to necessarily look where you're touching, just to avoid bias of maybe subconsciously gravitating towards a particular, larger particle or something like that. So, you do that for, typically a minimum of 100 count data points. So we went every 6 inches for 50 feet to achieve our 100 count points. And you can assess substrate kind of qualitatively, bedrock, cobble, boulder, small gravel, fine sand, etc. Or, you can assess it quantitatively. So actually, let me see if I can pointer options, laser pointer. There we go. So for each of these categories, there's a range associated with it. You can take the average of the largest and smallest and kind of get a mean particle size, and then assign that, to the particle that that you've recorded, and then over that 100 data point suite, you can take an average particle size for that transect, and those are assigned from an old geologist from USGS, Wentworth, back in almost 100 years ago, but rocks haven't changed in 100 years, so there's a again, there's a standardized particle size distribution that people refer to. So what do we see? So this is what I'm going to call the qualitative aspect. So this is the substrate composition by site. Most of these graphs moving forward are going to be in the same kind of format. So I'm going to have, the sites on the x-axis, generally grouped by the West Branch and the East Branch and Lower Beaverkill, and then the main stem, moving from left to right in kind of a downstream progression, relative to each of these subsets. And then on the y-axis here, we have just the percent composition in each of these locations. So again, we have 100 data points, and it's just a matter of, what proportion of those are cobble, gravel, sand, etc. And so right away, you can see that, just visually, these graphs are all pretty similar. You're obviously going to expect some natural variation in any system. But we have a pretty similar habitat across the basin, and it's all in pretty high quality. I mean, ideally, you want this mix of kind of cobble and gravel substrates that's going to optimize the the spacing in between the rocks that can that the invertebrates use to hide in and feed amongst. And so this not quite a mirror image of each other, but probably as close as you're going to get for, again, just being in the wild. So it dominantly the the instrument habitat's dominated, by cobbles and gravels. If you're fishing a lot, that's no surprise, but having something presented like this, kind of, it just helps, understand how the systems, compared to each other. If you wanted to look at it quantitatively, again, you would take, for all those 100 data points, you'd have an associated particle size and you'd average that across, through replicates and get a site average. And again, you can see these hover, the mean values are the points, and the lines are your standard deviations, standard errors. And so you can see these hover, quantitatively pretty close to each other. And, they're also hovering right along this gravel cobble interface, which is again, kind of your, some of your kind of your optimal, quality habitat area, kind of the, use a planetary analogy, kind of the Goldilocks zone. If you get, too fine a particles, sand and silts, we all know that's not favorable. If you coarsen and get into big boulders and bedrock, I mean, as you know, from you're a fisher person, that's not ideal habitat either. So, so both from a qualitative perspective and a quantitative perspective, these are all effectively similar. And kind of the null hypothesis moving forward would then be that we would expect a similar invertebrate community across, this upper basin. We don't see any habitat limitations that would suggest, differentiated communities at one point or the other. They all have optimal and sufficient habitat to persist in or at. So then, let's see what the invertebrates tell us. So our macro fuel and lab methods, given that it's a stream free-flowing system, we used what's called traveling kick sample. You stand in the stream, disturb the substrate upstream of your DNet. That dislodges the invertebrates. They flow into the net. You standardize your effort for 5 minutes, kind of per sequence, per replicate or per actual collection. If you're persistent in your pace, then if you standardize your time, you'd be roughly sampling a similar area, across all of these sites. Then we take that kind of raw sample, put it into ethanol on site to instantly preserve things, bring that back and sort. In this sorting pan here, you can see it's kind of gridded. So we dump what I call the raw sample into that pan, spread it out so it's evenly mixed. Things are randomly distributed, and collect 2 100 count subsamples. So you often don't go through the entire sample because it's just it would just be overwhelming. I mean, there's probably thousands of organisms in there, and if you're trying to pick out thousands, that would take a really long time. But if you subsample your collection randomly, then laws of statistics, your random encounter probability is going to be about similar to the abundances. So we took and so there's 20 of these grids, for each sorting. You kind of generate a random number between 1 and 20 random numbers. Let's say, and you want 100 subsamples. So I'll go to, number 4, I'll pick through that. Maybe I'll get 35 organisms. 35 isn't 100. Okay, what's my next random cell? It's maybe 14. Okay, I get 35 more organisms. That's 70. Okay, here I get, 15, and then there I get 15, just to make the math easy on me. So, okay, I hit 100. That's my subsample, and then I generally save the remainder just in case there's, something spills or something later on. You could resample if you lost your original sample, but but that's kind of the, and so we picked out two 100 count subsamples in each of these, one of which I'll identify more to a finer level to genus. That's going to take a little longer, but it matches what DEC does so that we can compare apples and apples to prior DEC data. The second subsample was a little or coarser ID just to the family level, which is quicker, which is what I'm presenting here, just so we'd have some semblance of, some results kind of midway through, and we didn't necessarily have to wait, the full 11 or 12 months to see what was going on. And then, oh, yep.
Quick question. Are these samples while the insects are alive, or have they died before you're able to?
They've died. So once I collect them in the net, we sort out any big obvious thing like twigs and bigger rocks, and we preserve all of the samples in ethanol right at the stream site. So they're
Okay.
it's curtains for them, pretty much right away.
Gotcha.
Yep.
Gotcha. Thanks.
Yep. And then from these subsamples, I'll then enumerate an ID. I'll pick out just the organisms and have those, in their own vial and preserve them with they're archived long-term and 70% ethanol. So we went out, collected from that, we sorted out all the, the actual biological individuals, and we have two subsamples, one of which is going to match DEC data, one of which was a quicker family level assessment, which is what I've completed now. And, we have everything, preserved, and archived at this point from the field effort. So what do we know? So it's gonna be a little confusing. So the first subsample is still untouched. That's going to be the DEC data, which is going to take me longer, which is what I'm going to do here January and February. What I'm calling the second subsample is what we're presenting now. So, and again, it's the same number of organisms in each subsample. This, I enumerated it and ID'd them just to the family level, which is something I could pretty much just do by site. So, I could process, 36 samples, in the course of, a month and a half or so. So what we see here, again, on this x-axis, we have the same naming convention and kind of organization across the West Branch, East Branch, main stem sites. And these are the broader, say, ordinal abundances. So, insect orders are kind of like your broader categories, mayflies, caddisflies, beetles. Midges are actually the family, but there's enough of them that you typically tend to break these out. Different crustaceans, amphipods, isopods, mollusks, freshwater clams, any freshwater mussels, snails, and then a spattering of, just random other things. So, and again, remember from our, substrate kind of hypothesis or null hypothesis is that we have uniform high quality substrate across the reach. They're not habitat limited. We would expect to see kind of a homogenization of their populations if there are no other factors than habitat limitation. And so immediately we can see that going downstream from Stylesville to Sheehawken, you know, there's a very clear shift in macroinvertebrate, you know, community assembly, right? So it's Stylesville, extremely few mayflies, very few caddisflies, beetles, stoneflies. I mean, these are you know, these four are kind of like your, you know, ideal, you know, preferred community or taxa. We see mostly midges and true flies, which are like black flies, which is mostly what these are. You know, crane flies, other you know, fixed wing flies that have you know, aquatic larvae. You know, quite a few crustaceans, isopods, mostly amphipods. You know, oligochaetes, aquatic worms, and you know, but obviously a dearth of, you know, what would be probably considered, especially your fly fishing, you know, the common stream insects that, you know, most people associate with, you know, any flowing water. Now, as we get to deposit, you know, it improves slightly, but you know, you still have this broader, you know, dominance of you know, flies and midges and non-insects. And then you know, the mayfly population comes up a bit to Hale Eddy. You see kind of these other organisms begin to collapse. And then at the very lower stretch of, you know, the West Branch, we start to see kind of a normalization of the community where, you know, the caddisflies are starting to hold their own. You have beetles, stoneflies, you know, and the midges are kind of been capped out at around 20%. If you kind of leapfrog kind of to the main stem here, you can see that, you know, the system is kind of normalizing to this, you know, roughly 30% mayflies, you know, 40% caddisflies, 20% midges, 10% beetles, you know, and so, you know, there's a clear signal, you know, as you go down the West Branch, you know, that something's, you know, clearly impacting, you know, and influencing the community. On the East Branch, it's not quite as, you know, I'll say, dramatic. I mean, we do have, you know, about 35% mayflies, and that holds fairly consistent kind of through Dan's and Glenn's house, you know, and then, you know, as you get, you know, much further down to the main stem, again, you kind of normalize to this kind of general distribution here. We took a sample at the Lower Beaverkill because, you know, the Beaverkill is uninfluenced by the releases. It's kind of the natural system, and you know, it kind of offered a kind of a unique, like, experimental control type of situation where, you know, if you didn't have you know, the cold water release, you know, what would your community, you know, look like kind of at that point, you know, in the basin. And this is about the first riffle upstream of the, you know, the junction there. I guess it's at the East Branch. So if you go over that bridge, yeah, there's a little, I don't know, little just built up area, and then you go up along the, I guess it would be the south or no, east side of the river, past it looks like a some type of construction or gravel place on the left, and you just get beyond where kind of the guardrail comes close to the river, and you know, there's a nice riffle there. So I mean, you're probably 300-400 yards upstream of that junction is where the site is. And so, you know, you can certainly see that, you know, there's a disproportionate amount of midges in the you know, that upper East Branch section, but that, you know, again, as you get downstream, you know, Downsville looks probably more similar to Stylesville than Glenn's and Dan's house look a little somewhat more similar to kind of what would be, you know, what the community that the river's trying to, you know, optimize itself on. And so, you know, okay, so we see a very clear trend here. In abundance, but then the next question is what is, what is the the diversity of each of these groups? So so if we
Whoop.
oh, did somebody have yeah, go ahead, Walter.
Yeah, could we go back a
Sure.
slide?
Yep.
I'm curious why some of these don't run at 100%. For example, Stockport.
Yeah,
showing
it's
only-
just an artifact of the averaging. So each of these sites has 3 replicates associated with it. So there's an abundance value. There's each 3 replicates, say it's Cheokan has an associated mayfly abundance. If you take that average, the averages don't always add up to 100 because you're obviously some averages are slightly higher than the sum and some are slightly lower. Does that make sense?
Okay,
Yeah,
that's fine.
it's there was 100 organisms out of each replicate. So each of these has plus or minus 300 organisms over the 3 replicates per site. But once you average the mayflies as a group, the caddisflies as a group, the beetles as a group, that average is kind of up and down a little bit. So the sum of the averages doesn't always add up to 100, but it I don't know. Yeah, does that help?
That helps.
It just it's just a mathematical artifact. We didn't sample or process Stockport any differently than anything else.
And smooth it. I have one other question.
Yeah,
If you look at Stylesville
yeah,
and Downsville,
yeah,
those are both pretty close to the dams and the outflows.
yeah.
Water is very cold there. What do
Yep.
you suppose? Now, this is just asking you for conjecture here. Why at Stylesville is there so small a number of mayflies as compared to Downsville?
I'm getting to that.
Oh, okay.
Yeah.
Great.
But I think it will be it's worth noting that yes, you do have categorically more mayflies on average than you do at Stylesville, even though temperatures are going to be similar. But there's a hidden story to this as well, which is actually I'm going to get to kind of on the next slide. So these are your mean abundances. So the question is, how diverse are each of these groups? Because that's kind of the next question. I mean, you can, as you guys know, there's different hatches over different time periods, but if you have different hatches, it means you have different groups of different families or different species. So if you look at this not from an abundance perspective necessarily, but a taxonomic richness, and again for this second suite of subsamples, I only went down to family, not to genus. So each one of these family groups can have as many as like 2 to 5 different genre, but again, that's for next spring. And again, you see a similar trend. So if you just look at the broader family richness of every type of organism, whether you're a snail or a mayfly or an aquatic worm, if you just pool the total, mean family richness of each of these sites, you're seeing this kind of upstream to downstream trend, similar kind of in some of the population, just the abundance data that you saw in the previous slide. So each of these points is the mean value from the 3 replicates per site, and then your error bars are the lines. So we can see that the macro population as a whole, regardless of what type of organism you are, is relatively depressed upstream in the West Branch here. And again, the naming convention on the x-axis is the same. I just had to kind of abbreviate it to collapse these graphs. So we see a slow improvement in overall family richness. As you go downstream on the West Branch from Stylesville to Hale Eddy to the lower, right, the lower part of the lower west. Downsville, again, you have a depression in overall macro richness, and that begins to improve. By the time you get to Glenn's house, Den's house, maybe I'll just call them the houses. The Beaverkill, lower Beaverkill here is up around 16 or 18. And then you can see there's kind of almost an asymptote or kind of an optimal maximum family richness that kind of the lower, or I'm sorry, that main stem segment, kind of it starts to normalize what's probably the carrying capacity of the river. So if you extract just what we're calling EPT family richness, so that's mayflies, stoneflies, caddisflies, kind of your cool water, sensitive taxa. You see an even more dramatic, kind of pattern, where, you're going from, only a couple, families spread out throughout those three groups, and that improves as you go downstream. And again, you get to, the main stem, you kind of on average normalize out to 10 or 11, taxa, EPT taxa, but, again, you're, by the time you get there, by the time you recover from each of these branches at the West Branch or East Branch, it takes you to Hancock before you get there on the west, and you're maybe 2/3 the way there. By the time you get past the houses. And so from this, if you extract out just mayflies, you can see at Stylesville you only have primarily one, maybe one other mayfly taxa. So Ephemeralidae, and I think there's a couple of betids. And so, but when you get to Hale Eddy, you almost, double, your richness. And, by the time you get up to, these two sites, which are pretty close together, you kind of, you're at about 4 families. Similar to Downsville, you had more mayflies at Downsville than you did at Stylesville, but you still are generally, only have about 2, on average 2 taxa. So even though you have more mayflies, you don't have more diversity there. Personally, I think that's the reason you have more mayflies might have to do with almost a thermal mass effect. You have more water coming out of Cannonsville. I think it's around 500 or 600 CFS. I mean, that's a lot of cold water. I think you only have, correct me, Jeff, is it 185 out of, or 85 out of Downsville? So you have a lot less cold water. That's a less thermal mass. It's more susceptible to daily warming, more susceptible to influence of incoming tributaries. So I think there's a bit of a buffer issue or benefit in the East Branch is why you can tolerate a little bit more of abundance and slightly more diversity. My Downsville site was right off that, I guess, a covered bridge park there. On the far side of the river, there's a little tributary that comes in there, as I'm sure you're all aware. When I was sampling there, I think the temperature, in kind of the proper main stem was, water temperature was either 48 or 52, something like that. But then that little tributary that comes in was 78. So, if that tributary is coming in at, 6 CFS or something, that's, or, 3% of your flow, being warmed, and 10 little tributaries is 30% of your flow, that's going to influence, East Branch, just from proportions more than it is the West Branch.
So
But, you know,
Jeremy,
it's-
is that, if I can, that's possibly the answer to Walter's question. Walter, you picking that up? The
Oh, yeah.
volume, it's
Yeah,
the
yeah,
volume
yes,
of
I am.
cold water in the West Branch keeps it colder, basically, and the volume of water in the Upper East is smaller, so the warmer tribs have more of an impact. Is that what you're saying, Jeremy?
Yeah, the warmer tribs and even the daily, you know, solar loading is gonna, you know,
Yeah.
bump it up further. So, invertebrates are exotherms, fish are exotherms. You know, their metabolism is going to be tied to their external environmental temperature. So, you know, as you have a warmer or even a broader temperature change or range throughout, say, the day or some particular time period, you know, that range, you know, is extended, then you're more likely to meet the metabolic requirements of more organisms, you know, that are within that range. If you have a very narrow temperature range, then you know, you're going to be limiting a lot of organisms that have metabolic requirements that are outside that range. But if you have a kind of a broad temperature gradient, even throughout the day, you know, some of those organisms are going to be able to metabolize ideally some of the time, if that makes sense, over a broader gradient. So if you look at caddisflies, mayflies and caddisflies, as you saw from those graphs, and midges are probably the three most dominant population-wise organisms. So that's the ones I've focused on, just because you have enough data to make statistical, you know, conclusions. You know, stoneflies, even though they're relatively important organisms, you know, they're pretty low density in general. You know, if you start just comparing ones and twos and threes, like your error bars are always going to overlap, and you're not going to really be able to you know, conclude anything. But, you know, the caddisflies are even more impacted by the colder water, you know, than the mayflies. You can see, I mean, this you probably just put in a textbook. You know, as you go from Stylesville Deposit, Hill Eddy, down to Sheocken, and likewise from Downsville, you know, to, we'll say, the houses, and, you know, Beaverkill, of course, is warmer, so that, you know, and then you know, the main stem sites, a little more variation, but in general, you could probably average them in the lower Beaverkill to kind of, again, a system optimum. Again, getting back to the you know, the cold water and the you know, the metabolic needs of exotherms. One of the reasons that caddisflies are going to be more affected, as you guys, you know, likely know. So caddisfly is a complete metamorphosis. Holo metabolus is the term. You know, they have those 4 stages. That takes more resources, more metabolic effort to go through each of those stages. Mayflies are, and stoneflies even are, you know, incomplete metamorphosis. So hemimetabolous, you know, they don't need those additional metabolic steps to go through that third life stage. And so, you know, the cold water, which is going to limit, obviously, as I mentioned, you know, limiting metabolism, you know, that's going to be a harder hit for caddisflies. And I didn't plot beetles, but I imagine the beetles would be show a similar trend, because they're a 4-stage complete metamorphosis organism as well. So, you know, across, you know, richness of multiple groups, we can see a very clear trend. It doesn't really matter. You look at all the organisms combined, preferred organisms, and, you know, mayflies and caddisflies. So there's a very clear, you know, site level pattern going on here. That's indisputable. So as we've all kind of danced around the elephant in the room, you know, the obvious variable in the system is temperature. We know those differences aren't habitat related, because we verified that the habitat is similar. So I went in and got USGS stream gauge data, you know, which correspond to some of the macro sampling sites. the 2023 data wasn't always available for each of the sites this year yet. Some of it wasn't, they only had it uploaded until like January or March. So as a placeholder, I went back and I looked at, I brought in 2022 data, over the growing period that, growing season that we wanted to look at. I calculated, average daily water temperature for each of these sites. And I also calculated cumulative water temperature degree days. Degree days are kind of a phenological variable. Most of the people are familiar with it. If you garden or plant people, right, you need so many degree days before, like, leaf out on trees, or, your tulips come up every year. If it's a warm spring, you build those cumulative days sooner. If it's a cold spring, I don't know if tulips, but whatever, tulips come up, later. So it's kind of a biological metric that is tied more to metabolism than water temperature, which is kind of a human artifact of what we're just describing, something. And so I plotted the time series water temperature profiles across the two main branches. And then, plotted the average temperature metrics against richness and abundance results. So, the elephant in the room's been anecdotally temperature, but do we actually see any sound objective data supporting that? So, this is just the West Branch temperature profiles from May to end of October, kind of the general growing season when you have the most biological productivity. And, you can see a very stair-steppy increase in average daily water temperature, throughout the year as you go downstream. So, Stylesville, is the coldest, and then, Hill Eddy, Hancock West Branch, and then Lordville, kind of just below our lowest site of the main stem. And, so pretty much during the, the summer here, there's a very clear temperature difference, temperature gradient as you go downstream. I think Jeff mentioned, the reservoirs turn over at some point in the fall, and then they all turn to, kind of low 50s. But, again, this kind of primary growing season, which is when, the invertebrates are, hatching, mating, spawning, laying eggs, and growing. We do see a very clear temperature signal across the reach. Similar to on the East Branch, Downsville is almost a flat line, which is surprising, well, at least for me, maybe not to you. And then, but what, you'll notice a difference is as you jump up to Harvard, which is kind of Dan's house, Glenn's house generally. And then Fish's Eddy, by the time you get to Fish's Eddy, Beaver Kill, they're all pretty similar. Again, I think this gets to the thermal mass topic that I kind of touched on earlier. All these little tributaries, daily solar loading, that's, you're heating up a third of them, or not even maybe a quarter of the mass that you are in the West Branch here. You're coming out, like, you're trying to heat up 600 CFS of water. That's going to happen a lot more slowly over time than, if you're heating up a quarter of that much water. So, we still see a temperature profile difference. It's much more, you reach an optimal temperature quicker in the East Branch than you do in the West Branch. So, so we see differences in abundance and diversity. We have a clear temperature signal across, both of these gradients. And so if we plot, say, mayfly family richness and water temperature on the again, the x-axis is your standard naming convention. You have mayfly mean family richness, so average family richness per site with our with our statistical error bars. And then our second y-axis in this case, just to show different perspectives, I have cumulative water degree days. So that's if you're basically adding the average temperature each day, day after day after day. So and so you can see, and I'll say that the relationship between the blue dots and lines and the green squares is arbitrary. It's just how the axes line up. The fact that this one's closer than this one doesn't mean anything, per se. But what you want to do is just look at the two trends. So again, we see that the mayflies diversity goes up as you go downstream generally, and we see that the water temperature is rising almost at the same rate. Downsville, you have very cold water, you have a depressed relative to the East Branch, depressed family richness. As you get to Harvard and that water temperature increases, you see a recovery. You double your mayfly richness, family richness, just between Downsville and Harvard. And then again, the lower Beaverkill and the main stem sites, you kind of see again this kind of asymptoting or kind of system normalization, and our water temperature metrics are again somewhat similar. So we see a clear signal that colder water is depressing the diversity of mayflies in the system. And if you look at the caddisflies, again, same, mean family richness on the X, or I'm sorry, on the left, and cumulative water degree days on the right. You see that, again, it's almost a 1-to-1 correlation. As the temperature increases, more warm water over a longer time period, that provides, more metabolic opportunity. You get, so you get from your abundance graph, the panel, increased water temperature is giving you both more individuals, and of those individuals, it's more diverse. So you get kind of a, you improve in both, abundance and diversity throughout, these gradients. And again, Stylesville to West Branch Hancock, and then Downsville, middle East Branch, and then lower Beaverkill and main stem, things start to taper out and again normalize. But again, so now we see, a very clear temperature signal between mayfly richness and abundance, and caddisfly richness. So if we look at abundance, just of the mayflies, because remember that was kind of the inclusive in that multicolored panel graph. We see low abundance at Stylesville, improves a hail eddy, and then or lower in deposit hail eddy, and then kind of again normalizes around lower West Branch. And you can see that this is average daily water temperature. Again, it's just a different metric, but to show that both of these metrics are behaving in a similar way, that it's so you as you increase your average daily water temperature per site, you're improving mayfly abundance. On the East Branch, you have a little better on the abundance side of mayflies, but remember that's a pretty depauperate richness. So you're basically getting, only ephemeralidae. So even though you have more, you only have more of one thing. You don't have more and more of, 6 things, for instance. And then, as you get to, the lower stretch, you know, they kind of normalize at, you know, roughly 25-30%, which seems to be the kind of the community optimum. Uh, Similarly to caddisflies, again, almost, you know, you put it in a textbook, improve, you know, slow improvement as you go down the West Branch, and again, an improvement as you go down the East Branch as temperatures increase, abundance increases, and again, you get to kind of the lower stretches, and you know, generally they kind of optimize at this, you know, roughly 35% of the community. And again, so you know, now we see, or, you know, objectively can document that, you know, water temperature is strongly influencing both richness and abundance of you know, all organisms, and particularly we'll call kind of the more important organisms, especially if you're a fly fisherman. You know, midges, I threw it in there just because they are another abundant organism. You actually see a bit of a opposite effect. So, you know, as the water temperatures goes up, you know, the midge populations, you know, are either static or go down a bit. And you know, you can see that pretty clear here, you know, juxtaposing the main stem beaverkill with some of these other sites. I think this is basically a competitive advantage trend. So, you know, when it's colder, other organisms can't you know, compete as well, and so, you know, you don't have as much competition across the invertebrate taxa, so certain organisms can, you know, be more abundant just because they're not competing. As you get to the warmer temperatures and other organisms can now operate in their metabolic optimum, you know, they can actually hold their own and start, you know, pushing some of these other organisms out. So as you see down, you know, in this, you know, the lower segments, you know, we know the caddisflies had improved populations, the mayflies have stabilized, you have more beetles, you know, all those organisms that couldn't persist in colder water, at least persist you know, comfortably, you know, can start kind of pushing the midges out. But again, considering they're probably the third most abundant organism throughout the reach, I thought I'd just, you know, add a slide of them just to be, you know, inclusive and show that, you know, there are, you know, other water temperature gradient, you know, other responses beyond just decline.
Hey, Jeremy, it's Jeff. We've been at this for about an hour. I just want to check in with the group. And if you got
I
any-
think,
anybody
yeah,
heartburn?
I've probably got about 4 slides left, so I'm
Okay.
almost. Yep.
Great, thank you.
And so if we just wanted to, again, look at some of these values and juxtapose just the richness values on the sites that we have our water temperature gauges. So on each of these, this is that similar 4-panel richness plot, and all I'm doing on the x-axis is average daily water temperature, and on the y-axis is the various macro diversity metrics, all family diversity, you know, the EPT, mayflies, caddisflies, and you can see these are all significant, strongly significant, you know, trends. You know, if you're familiar with statistics, your R squared is kind of the percent of explanation between your two variables. You know, here's a trend in our mean family richness. Overall, water temperature explains 80% of the variation. You know, 92% of the variation in caddisflies, and not quite as much as mayflies because they're, you know, they can tolerate you know, lower temperatures, but you know, there's still you know, a decisive significant trend between water temperature and overall macro diversity. You know, if you look at the water temperature and abundance correlations, you know, the mayflies, it's actually non-significant. It again, they're, you know, the Downsville is, you know, kind of your outlier there, but you're getting, actually, I think it's right here, but it seems like if you look at some of those, the system wants to kind of normalize mayflies, at around 35%. And so I think something like Hale Eddy, it's kind of an inflection point because, you've bumped up your temperature enough to increase mayfly abundance and diversity, but not enough that other organisms can, be in their optimal range. So, and so I think in some of the cases you're kind of artificially a bit higher in the cold water, but then you kind of normalize as a system that, roughly 30% mayflies. Caddisflies, again, more strongly affected by the temperature, in part because they're metabolic, life stage requirements. A very clear trend with caddisflies in abundance. Midges, I didn't even put it in here because they're pretty much flat, but broad summary of 2020 sampling efforts so far. It's probably likely the most comprehensive single year macro assessment across the upper Delaware, kind of a perfect storm of replication, longitudinal breadth across the reaches, and an associated habitat assessment. We developed a sound baseline set of macroinvertebrate data, allowing statistical comparisons across sites, and then again to be continued later. Once I get the first subsample set done, we can actually compare all the historical DEC data and test whether a particular data point in history is significantly different or not from what we see today, and demonstrate a very clear water temperature effect on overall macro abundance and family level richness, diversity, along these multiple kind of river sub-basin gradients. What remains now for kind of the remainder of phase 2, this next few months, that first subsample that I mentioned will be ID to genus, or in some cases just the lowest practical taxonomic unit. We can then use that data to compare to the prior New York data that was showcased in the phase 1 to statistically test historical trends in abundance and richness. So that arbitrary data point at Downsville from 1993, we have our range now, statistical range. We can do a statistical test, is that value inside or outside of what we see today? Another thing that Jeff mentioned in a prior conversation is along with temperature is the actual discharge volumes. I can extract similar data that I did with the temperature data, and we can test whether, is there, does discharge, show any influence on these on top of temperature, and kind of a final, broad report, compiled, late spring 2024 with, a summary of all the results, conclusions, and, recommend recommendations, for future macro information needs. What's the value in continuing to support this? Is there any, what could we do, at least in the near future? There'd be an opportunity to tighten the data and further solidify temperature or potential other factor narratives with some additional sites.
Fishes
In
Eddy.
2024, I'd like to have a site at Fishes Eddy where that gauge is, and then the Upper Beaverkill, which is not influenced by temperature in a similar way to Downsville, is that would help again allow that kind of natural control experimental setup where if you have you could really examine how depressed Downsville, for instance, or Stylesville would be if, if you didn't have the cold water influence, or at least hypothetically. It's gonna allow for accurate, and building this out will allow for accurate monitoring of macro populations in future studies, potentially in response to unknown factors, whether it's climate change, maybe some future energy extraction. I know fracking has kind of been off the table, but who knows, maybe there's some new thing that people want to, engage the landscape on in a less than ideal way. You'd be able to have baseline data from prior to any perturbation. This is actually, as I said, really good. Let's put some of this in a textbook. I would look to potentially actually publishing some of this in a scientific journal or journals, depending on the final suite of data gets set. But I mean, this is actually surprisingly robust data for what we have. And then more broadly, can help ask the right questions. And if you're engaging with various resource managers or stewards of the river, if the water temperature is limiting the macros, and we clearly show even preliminarily here that it is, and you're limiting the trout forage, what other effects may be occurring? If you're limiting the availability of insect forage, are the larger fish shifting to piscivory? Are they eating more fish, more younger trout? Again, fish and macro invertebrates are exotherms, or metabolic growth and activities tied to water temperature. Are you stunting the growth rates of younger year trout that are being spawned in these upper sections of the river? Are you getting lower length and age rates, depending on where you are, where you were spawned in these systems? Does that equilibrate to lower fishing quality between lack of bugs and potential lower growth rates of trout? And then does this water temperature effect, is it just an additive stressor for other potential factors in the system independent of, say, just water temperature? Road salt runoff, different discharge regimes. It's like, if the invertebrates are already kind of getting hit from a couple of different sides, is the water temperature limitation just another stressor to add on top of a cumulative list of stressors that might be influencing the invertebrate population now and potentially in the future? So
Jeremy?
with that, thank you, and I'll take questions.
Can I jump in with a question?
Absolutely.
Is there some way to measure the total abundance on some scale, like per square foot of river bottom or volume of water flow? Because I fish a lot of midges, actually.
Yeah.
And the density and availability of midges upstream near the reservoirs may offset the fact that there are not as many mayflies or caddisflies there.
Sorry, I don't know if you're. So there is, as far as sampling methodology, there's something called a server sampler. It's a standardized area. It's kind of a frame sampler that you put on the riverbed. You have a standardized area. You collect everything within that square frame that goes into a net. And so, you could standardize your collections and get density, density values. So that's, so that's a common, a common technique. As far as your midges, I actually had this conversation. Speaking just kind of hypothetically, I had this conversation actually with somebody looking at ironically bird diversity in some of our dam removal sites that I oversee on the main project I work on at Cornell. And one of the kind of the foraging efficiency conversations we had was a midge, an adult midge, or even a larval midge is probably a 10th to a 50th the size of a mayfly or caddisfly, right? So
Sure.
if you're a bird and you have a certain forage requirements or biomass requirements that you need to feel satiated or sustain a certain growth rate, it takes effort to catch obviously anything. And so if you have to go out and capture 300 organisms and expend effort capturing each of those 300 organisms versus 20 organisms to gain the same level of biomass or to ingest the same level of biomass, that I'd imagine it would be a similar situation with fish or trout or anything, where if they have to sit and sip 300 midges to gain, I don't know, 100 kilocalories, or they can eat 10 mayflies and gain 100 kilocalories. They're spending more effort getting the 100 kilocalories out of midges, so their net
Sure.
net growth or something is going to be reduced. That's just a hypothetical thing on my end, basically, but that's how I would start to approach a question like that.
Yeah, I would be curious to see how I don't know, by weight or, how many ounces of biomass, insect biomass is in this square foot here versus the other sites.
Yeah.
But that
there is, again, I think the problematic aspect is that they didn't do replication, so it's just single data points. But maybe we can follow up later. There is a national park study that I'm blanking on the national park guy.
Don Hamilton.
Don Hamilton. That sent Jeff and I that they did one of their studies did look at density. Although they had, I think, a couple sites in the main stem and only one site on the very lower west and one site on the very lower east. But even then, on the lower west branch, you did see a decisive density decline. So maybe we can, at some point, follow up with you, or I can remind Jeff, and he can either send you just the figure or the paper, and you can see that. But there is anecdotally, there is evidence that shows like a density decline as well, not just abundance and richness. Dan.
Hi.
Yeah.
First, I wondered if you could take down your slide presentation so we can see each other.
Oh, sure.
If that works.
Yep.
Great.
Okay.
Thank you. So I have hey, East Branch buddy. So I have a lot of questions, but one is, I know that Jeff and all of us have been asked for a long time as FUDR officials, is how do you have any insight after doing this as to how the insect abundance and diversity has changed from, say, 10 years ago till now? Because, we'll hear guys say, oh my God, there used to be so many such and such bugs here. And also, it's a second question, but if you have any input on a lot of it is blamed on flooding, So I don't know if you have any thoughts on that.
So, with respect to the historical comparisons, I will be able to answer that question, but it'll be kind of maybe in a final presentation. So to match the DEC data, I have to ID the bugs down to the same level as so we're comparing apples and apples.
Right.
And so that first subset is what I'm going to be going through here this winter. So I can't answer that right now, but it's something we will be able to answer, here in the future. I did this first kind of family level quick ID subset, just so we had something to talk, like, do we even see anything? Which we obviously do. And I will say that just, I think some of these trends are even gonna be more disparate as you get further down into taxonomic richness, because just my own familiarity, some of these, even though at the family level, like from Morellidae, I can be like, oh, here's 5 genus that, I know are there, but just aren't reflected in the data. So, I think some of these, especially richness and diversity trends, are even going to be more dramatic, where you're going from 1 or 2 genus to 8 to 10 genus, further down, depending on what your gradient is. So, did I answer both of those?
Yeah,
Okay.
that's pretty good. I thought that might be the case.
Yeah.
It's a lot.
Yeah.
But yeah, so that's what we get hit with, 10 years ago, it used to be so much better, or even 2 years ago, it used to be so much better. Then the high water came through, or,
Mhm.
they did this work on a certain creek and all of the sedimentation came in.
You know, a similar
Yeah, so
question.
like if you, with those, oh, sorry, let me just, so the benefit of this is, we saw we have a number of those plots, right? We had a mean point and then this, the error bars, right? So, as long as you're comparing apples to apples with the finer taxonomic data here later on, we can take one of those, DEC points as, and say, oh, they found, 12 mayflies, whatever, in 2006 at this site, right? So, then you can statistically, test whether, is 12 within this range or not. If it is or isn't, then you can go to your respective conclusions. But yeah, we will be able to do that.
Okay, great. Thank you.
A similar question comes up. I have a lot of friends who say, oh, the Farmington is operated much better on a reservoir level than, what happens in our
Mhm.
Is there, and that's just one example, but are there any examples of other below reservoir systems that have data like this? I mean, your data is wonderful, so that we could kind of compare reservoir operations at all.
So I know there are studies. So the short answer is yes. I haven't, because most of the work that I've done, at least last few years with Cornell and the dam removal work, or mill dams and they're, run a river spill over the top. So it's not the
Right.
same system, but like I do know from certain studies, I think there's one in 2021, I think it's Zaida et al. That showed that, I mean, it's a warming effect because these are spillover, but they put data loggers, I think, 12, 15 miles downstream, and you could see that, there's this strong temperature gradient as a result, in this case, of the warm water on top of the pool, elevating temperatures as much as like 10 to 15 miles downstream. So they kind of refer to it as like a dam shadow effect. And so, but I'm generally aware that there are studies that have looked at deep water releases more so out west, because you have a lot of those like in Utah and Arizona, and that looked at macroinvertebrate diversity changing over the period of or over the reach of a tail race, for instance. But it would be, I mean, whether the metabolic rules are the same whether you're in southern Utah or upstate New York. There is going to be kind of a governing effect of that on aquatic life, exotherms in particular. So
Walter's comment on midges is interesting too, because now that I'm out west, you go to the San Juan River, and it's huge trout that are feeding off of nothing but midges.
Absolutely.
And I hadn't really thought about fishing a lot of midges underneath our tailwaters, close in. But it's a really good point, and the midge population is obviously quite large there.
Actually, in the San Juan, there's lots of scud and worms also.
So that's very similar to below Stylesville. And so what you also might just be observing is just an artifact of, the other, we'll call them preferable organisms, just can't persist there. Right. So, yeah, that's what they're eating because they don't have a choice.
So, I know Joe Ansher, looking at as another neighbor on the East Branch, is saying that he feels a lot of the reason the juvenile fish in our system aren't surviving because there's a lack of structure. What about, is there I've never heard anybody ask, can we improve bug life through some artificial means? When we're doing stream restoration or it's always about habitat. It's never, how do we get more food in the system?
Yeah. Yeah, so I think a big valuable piece of this is that we do have a habitat component, and we see that you do have good quality habitat throughout. So you're not habitat limited.
Okay.
And so I think, I'll look at discharge, here, but I do think it's, kind of Lord of the Rings analogy. It's like, temperature is the one to rule them all. And I think what is valuable and showing some of these gradients is, again, again, it's not, you guys are all more familiar with this than me, but to the extent that any of these release regimes are negotiable at some point in the future. I mean, I think what you could, if you go back and look at some of these panels, you're going from like an average of like 48 to 52, say, for instance, or 55. And, but you're seeing a disproportionate improvement even over that gradient in richness and in abundance. So, I was telling Jeff, like, hypothetically, just to develop the argument is, if they could, say, spill warmer surface water, I mean, it sounds like they can't, but again, for the argument's sake, if they could spill surface water to normalize the water temperature, let's say, they have to give up 5% of their flow to spill water to bring the water temperature up 5 degrees. It's like, okay, you're giving up 5%, but you're gaining a 400% increase in macro, robust community robustness. Just so, I don't know, you can see my point there, but I think that kind of gets what you were saying about.
Walter disagrees with that. The reason Walter disagrees with that is because this is a continuum. If you put warmer water out of the reservoir, it's going to result in warmer water temperatures downstream, which is not necessarily good for the trout. I agree with you, the water coming out of the reservoir on average is extremely cold. But as it moves downstream and picks up these tributaries that you mentioned, and just the normal climate warming, you get to ideal trout habitat. And you get too far downstream and you lose good trout habitat.
Well, I think
I would just caveat by saying you have excellent adult trout habitat. I think you're depending on how
it's okay if they want
a suppression of, say, growth rates of juveniles. I mean, that's just like a metabolic fact. So yes, you have an ideal adult trout fishery. These adult trout that might be spawning in these upper reaches, the egg to juvenile proportion is going to be lower. The growth rates of the juveniles to grow out of a predatory prey state are going to be slower and more, less effective. They're going to put on weight slower, unless they maybe go up into some of these lower tributaries as like a inverse thermal refuge. So, I mean, there is kind of almost a have your cake and eat it too. You're not gonna, you can, I don't want to say you can have one or the other, but there's, the lower temperatures is going to have a wide kind of call it like trophic cascading. So you have less invertebrates, that's gonna mean less forage for even the younger trout, not to mention how quickly they can put on biomass, which is gonna influence, how many younger trout build up to a certain age class, at least locally that, we'll call it favorable, but just, I think that's a worthwhile caveat. Go ahead.
Jeremy, one
Yeah.
question. Is there any consideration about doing any chemical analysis and maybe the influence of farms, which are predominantly more existing on the East Branch as far as farms that are adjacent directly onto the rivers than it is on the West Branch? West Branch predominantly has more private homes, I think, and somebody can correct me if I'm wrong. But the East Branch has a considerable number of, dairy farms as well as regular farms along the, and I don't know if it contributes with phosphates or anything like that with fertilizers.
So there you could certainly, I mean, that's kind of what I hinted at it, maybe some future stuff of like, kind of additive stressors or, other factors that might be in play that, the other thing might be, kind of chloride and road salt effects as well, especially out of the reservoirs. Elevated salinity affects mayflies, more than other invertebrates. It's certainly a possibility, and it's a,
Pretty simple.
you could build, you could get, data loggers or grabs, you could develop a longitudinal chemical profile, to test, some of those and get, on top
Hey,
of.
Joe, Jeremy, I'll just jump in because I'm not sure
Yep.
if you're aware of it, but Science on the Fly, we've been doing water quality testing
Oh, that's
now
right.
for almost
Yeah.
3 years. So, and they just sent me a note wanting the rest of my samples, and they're prepared to give us a water quality update. on
Okay.
their
Yeah,
data.
I remember that.
Yeah, you should have, we'll make sure you get looped into that, Jeremy.
Yeah.
Dan, I'm sorry to
But
interrupt.
I will just, sorry, I just, maybe just quick, just, on a, as I mentioned, kind of the additive stressors, again, it could be something like, these colder areas, some of the macros are, kind of operating at like the margins of their metabolic capacities. If you stress them on top of that, the population, with, somewhat more salinized water or, higher phosphorus or something, I mean, that's going to have a kind of a ratcheting effect of not everything, you're going to have droppings out. Here's another additive stressor. Okay. 30%, 10% more of these just didn't quite make it.
Right.
So, just wanted to.
Okay.
Connect
Go ahead,
them.
Jeff.
Dan or Molly, maybe, do you remember, or anybody, you remember Cannonsville at one point was designated, I guess, by DEC or DEP as phosphorus problem, right?
Yep.
And I don't, does anybody have any memory of what that meant, if anything, for the discharge in the river?
Yeah,
I think since then they have cleaned up
Yeah.
has
Yeah,
it
so
improved it?
it was when Joe said talked about the farms on the East and West Branch, you actually have to look at farms above the reservoirs.
Right.
We're getting
right.
we're getting that water. So, the Cannonsville was always higher on nitrogen and phosphorus levels than Papacton. That's why, again, Papacton's considered the champagne of New York City's drinking water.
Yeah.
It's a lot more ag up there, but it has, you're right, Jeff, and Molly may know more about this than I do. I'm not sure at what level, but they really have improved the water quality of Cannonsville as well over the last 10 years or so.
Well, the other
Well-
thing that happens though, when we went to a cold water discharge, we changed the chemical makeup of the water coming out of the dams because the phosphorus and the nitrogen tend to be in the top stratosphere of the dams, and iron tends to be at the bottom. So you wind up getting more iron. It's the reason that we got the Didymo when we went to a cold water discharge, blooms, because we changed the chemical makeup. I don't know how that affects the amount of nutrients for the algae that the insects feed on, but that could be another possible factor in all of this.
Yeah. I'm going to jump in one more time, and this is, I promise, will be my last question.
Yeah, no worries.
Or comment, Jeremy, but I think that what you started to say, and Walter, don't beat me up. Walter's Walter's one of our biggest and best supporters and been on the river a long time. But I think it's exciting, Jeremy, to talk about, and Jeff and I have been laughing about this. Jeff is like, hey, Dan, what if all of a sudden we've got to start pitching our community that we need warmer water, right?
Mhm.
Warmer water is a solution to increasing the quality of our fishery. So,
But
so Walt, all I'm saying is that if we're believers in science, right? So here's science again. This is our
I-
first real
I agree.
shot at research. Maybe, maybe it is a way, if we're really looking at how do we make things better. And it might be an easier sell to New York City too, to say we just need more water, more cold water. Maybe it is a little, and maybe it's easier to get a little, I don't know, but it's exciting to hear that and say, oh, maybe there's a way. And it's about keeping the year of young survival rates higher. It's about, increasing the biomass of and diversity of the insects. That part all makes sense, and if it is from bringing the water notches up a little bit, at certain times of the year, right? We don't want to lose Callicoon. We don't want to lose Lordville, 60, those temps. But maybe
But don't you think a follow-up study for that would be tracking fish movement and migration when the temperatures are warm, right? Because the habitat doesn't change, the water temperature changes, right? The further you go down the system. So those trout clearly are way down in the system in the fall and the spring. So we need to get some science on where those fish go when the temperatures do warm up. And Jeremy, one question I have for you is, and this could be probably an hour lecture, but trying to come up with we're trying to come up with functional, practical takeaways from this, because the people that are putting money into it want to see how it can improve the fishery and essentially potentially get more cold water, whatever. But what percentage of the aquatic life hatching is temperature sensitive versus just maturation timing, right? Because in the spring we typically have an overabundance of Hendricksons right throughout the system, but I know those nymphs mature and it's time to hatch, and then when the water temperature drops to a certain right, so both go hand in hand. So I don't know, there's probably not a quick answer for that, but I guess at some point the temperatures in the fall and the spring sort of normalize, but you have a heavier concentration of certain macroinvertebrates in different parts of the system, which I know you got to take the whole year into consideration with temperature and substrates, et cetera. But just quickly, if you can, maturation meaning timing of when the sulfurs hatch versus the temperature it needs to get to, water needs to be for those bugs to hatch, because we've all seen in the summer when we're downriver and all of a sudden we get a push of cold water, all of a sudden there's sulfurs hatching everywhere in July. So is there a quick answer for that or no?
So yeah, the maturation, if you think of an individual bug, the maturation duration that it takes to mature from its immature stages and hatch out is entirely water temperature related. So if you're a mayfly and you're in 55-degree water, you're gonna take sooner to mature and develop than you are in 48 degrees. And it's the same, for say fish hatching. I mean, if you're familiar, if you read, blips on life histories of say rainbow trout, that they lay their eggs and, so many days at, 43-degree water or something, they turn into fry. Well, if you get warmer water that, they'll turn in, they'll add sooner. If you get colder water, that'll be delayed. So the same principle applies to, the growth, maturation of invertebrates. It'll also influence the, the fecundity, like the number of eggs, a particular female adult can produce while she's developing. Just for the sake of the argument, if you have a female mayfly that's developed, say, in 58-degree water, maybe she'll have 15,000 eggs. If she's in 48-degree water, she might have 9,000. So it really does govern pretty much all of their metabolic life stages. If you get, the other thing to consider, I think I mentioned this to Jeff too, is an aspect of more flow. You often see, you could see more, observe more organisms. But that's also because you're inundating more of the riverbed, and you have more surface area from which to, I'll say support or grow invertebrates from. So, that's another aspect of just, higher discharges or higher flows is, maybe you gain kind of, if you think about it, maybe you gain 15 or 20% more growing space, so to speak, on the, margins of the river that you wouldn't have on lower flows that will contribute to higher. So there's an improved flow component that's somewhat independent of temperature, but again, you can kind of go on, how do you optimize, right? You can have more flow of colder water and you'll get, some additional, biomass of invertebrates simply because you have more inundated water space that invertebrates can grow and mature under. If you had more warmer or slightly warmer water, you'd be able to maximize that growth over that period. Then, of course, if you get too warm, then you're going to start suppressing. So there's always going to be some type of, biological optimum, both flow and temperature. Again, where that is could be the hour discussion, but, you will have some benefits, if you have, just more water, that's going to be an improvement over, if you
Less
keep your
water.
other variables constant. So if that helps, I don't know if that helped answer
I
your
have a question for the group. I know there's some dams that are able to release water from different heights,
Right.
top, bottom.
Yeah.
Our dams have that capability?
I don't know about releases, but they do for
Yeah, I don't think so.
sending it to the city. I don't think so on the dams.
Yeah, they got it for diversions, but not for the bottom releases, unless you're spilling,
Right.
which is inadvertent.
If it's spill or bottom release, we don't have
No.
any option in the middle.
Well, there's siphons that are going into round out, but not on our reservoirs.
So
I-
Walter, you can relax. We have no way of getting.
Well,
normal-
yeah, no, I know Dan is gonna try and figure out a way, like the siphon. But
Dan,
you
let's
know,
talk
there's
after this.
there's ideal water temperatures for bugs someplace along both the east and the west branch because
Right.
of that cold water that starts and natural heating and.
Right. And you kind of see that, like, as you go down
Yeah,
that grade, you look at
exactly.
the main stem, like the system wants to optimize to a certain community, a certain level of abundance, right? That matches its carrying capacity. And so you start to see that coalesce further downstream.
And what you ideally want to do for us fly fishermen is increase the length of where we have ideal water conditions. If you heat it up more at the reservoir, you're gonna heat it up someplace downriver where it won't be
Right.
so ideal anymore.
I mean, I think, Jeremy, didn't I not see, I've seen this presentation twice now. I think what you're saying is you use the word normal, the bugs normalize somewhere in the lower west and the main stem. but
Mhm.
also in the lower Beaver Kill, right? That
Right,
you're
and
using
kind of
that
the
term
lower east from what little, kind of,
and the lower east, I guess. Yeah.
yeah,
Yeah.
so, and I will say that, again, just maybe just broader, kind of statements, but like, adult trout do fine, when it's, 58 degrees. So, we're not saying like you have to raise your water temperature presumably at the source so much that, you're at 82 degrees by the time you get to Lordville. What I'm saying is that you have there's a kind of like the medium porridge in the middle where it's like you could have, a few degrees more, 3 to 5 degrees coming out, improvement at, the sources. You're not going to have your top end values of invertebrates, but you're probably going to increase them by 300 to 400% from what they are. And, you're really not going to have a deleterious effect on the adult trout because they're still well within their kind of optimum of the high 50s, even if you get it, down further downstream. So there is a bit of a, everybody can have a piece if you try, if you can, and the others potentially, kind of positive feedback loops is, let's say you do bring it up 5 degrees or something, or 3 degrees at the reservoirs, then, you're increasing diversity and abundance of your invertebrates. That's going to increase the food source of those organisms in that reach. You're going to have higher growth rates, as well. And maybe one other final caveat on, just diversity in a system in general. Diversity also adds resilience to the system. So,
Yeah,
if you have, a pathogen or something, I mean, that, might come in and influence mayflies. If you only have one type of mayflies and there's a specific pathogen or environmental condition that they're acutely sensitive to that occurs, now you have nothing. It's an all or nothing thing. Kind of like a farmer that plants 12 different crops. I mean, maybe the weevils get his, I don't know, cotton or something, but then he still has 4 other things to sell. So, there's inherent resilience, in any natural system that you gain with just broader taxonomic and, diversity, that hedges against, catastrophic losses.
Yeah. Hey, I'm gonna do some housekeeping here. We've been at this for a while. I'm gonna end this at 1 o'clock unless anybody has a burning need to keep going or has any other questions.
No, I think it's excellent what has been done so far.
Thank you.
I think it's fine. Jeremy's done an excellent job there.
So Jeremy has some more work to do in phase 2.
Yep.
Phase 3 is several months away, should we get there. Thank you, Jeremy. First of all, we much appreciated. And I think you keep going, and this group will meet independently, I think, and talk about the future. We won't be able to do that before the holiday, but in January, I'll corral you back in, if that's okay, if that works for everybody.
I have one last question, Jeff, and it should be an easy one.
Sure.
So this is something that I know you too, Jeff, none of us have really been aware of, and I just stumbled on it years and years ago. But DEC, Jeremy, you probably may know about this better than anyone else. I met someone on the river from DEC, a woman, who told me that there's a cycle period, and I believe she said every 3 years we come back to the Delaware.
That's the
And-
RIBS program, Dan.
Yep.
Fisheries knew nothing about it at the time. We reached out to them. They didn't know that they were out there or who they were. And she said it was every 3 years. So I don't know but she mentioned that they were the only entity from DEC at the time that were doing insect studies.
Yeah. Before you got on the call, I think there was a slide that talked about the RIBS. It's the
okay.
rotational basin study that New York DEC does.
Okay.
Jeremy has all that, and Jeremy, I think it's fair to say it's I think it's every 5 years, and it's very sparse database.
Yeah, so it's good. I mean, I should qualify to, not knock like, the entomologists in DC. I mean, it's good, they know what they're doing. They're doing it standardized. The shortcoming though is, they only collect one, they go out, they collect their one sample, they analyze it. And they don't always go back to the same places consistently. So if you, I don't know if you, I don't know if you were involved with the phase 1 presentation or not, but if you remember, we have a plot of data and like pick a site, Downsville, the biomonitoring unit has been doing sampling since like 1987. And, they've been cycling through every 5 years, or, I think that maybe normalized in the last maybe 10 years as far as the 5-year cycle. But, they don't always go back to the same site. They, where haven't we been? Oh, here's somebody who wants to know about this. So, you get which is kind of, the biggest impediment to, the analyzing that work, which is kind of where we segued it, discovered this need is, you'd have a single data point, from like 1993, and then you have another one in 2006, and nothing after, nothing in between, and nothing before.
Jeremy, the reason I bring it up, because I don't want to drag this out here, because Jeff wants to wrap up, is an action item for us.
Mhm.
We now are starting to have some power and some say and pull over these studies.
Yeah.
We could go to them and say, this is what we want you guys to focus on. Here's where we would like you to go. Here's the places that Jeremy would like to see you guys do some work. Here's what we'd like you to focus on. So it's not so superficial and it's more meaningful to what we're doing. I think we could maybe have some sway in that.
Well, related to that, Dan, is Glenn, I know you've been a part of this. Joe, you've touched on this. DC's reluctant to accept citizen data.
Yeah.
Right now, Jeremy, I think you do have some sort of formal certification or something with DEC on some of your prior work, right? Like, wouldn't it be cool if we got what you've done even so far, entered into the record of the DEC? Glenn, you know what I mean? Like, haven't you?
Great idea.
Jeff, on the TU call I was on a few weeks ago with Steve, and it's recorded. He came right on and said, I am a big believer in citizen science and we need more of it.
Mm-hmm.
But they have these protocols, and Molly, I think you've seen some of that in your world too. Right? You gotta have meet certain standards, and I don't know whether it's training involved or certificates and licensing or what, but it's
just talking about red counts specifically.
Yeah, and I think they did
so
that.
I just say categorically, and again, I'm not some of the exact nuances I'm still uncertain of, but so for instance, for DEC to quote, use or accept, I don't the exact verbiage, like with the dam removal work, as far as instituting like dam removal policy or mill dam removal policy, as a lot of the work clearly shows that, oh, you take this old dam out and the stream gets better. But for them to be able to use that data to justify, a policy shift or even say, the ribs location selection might be a policy thing. You have to have an approved quality assurance plan that's accepted by DEC and their quality control agent that outlines. And I think I sent it to you, Jeff, a while ago. I mean, it's I had to put together like a 50-page document of where am I going, what are the literature justifications for how I'm sampling, how's everything standardized, data quality control, data preservation, blah, 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 blah. I mean, it's, of course, I will say that the dam removal work is something very unique, from what our research and collect, and how we designed the monitoring,
we won't be doing any dam removal up here in the upper Delaware.
Yeah. But where I was going with that is I think there might be maybe a kind of a corner cutting, if you will, and I don't know exactly how to articulate, well, how you'd articulate it to them, but if, you know, so this kick sampling is right out of their own stream biomonitoring protocol. So, you know, what I don't know is if can you create a document that basically, I mean, you'd have to, your sites and stuff would be specific, but otherwise, you know, say, look, what we're doing is you're matching your own document and as far as the methodology, and is that enough to satisfy, you know, your people to say that this is, you know, consistent in quality to your standards, like, you know, or do we have to like physically like rewrite a document that essentially is word for your own document that we're using? So
Molly, were you gonna jump in, Molly?
I was
Are
gonna
you-
say very similar things. Yeah. I mean,
Okay.
Jeremy did actually much more description than I could.
I have
Yeah,
one last
so
question.
go ahead, Glenn, go ahead.
One last question for Jeremy. So,
Yep.
you know, Dan brought up the deficit in the younger trout that we have on the east branches compared to the west branch.
Mhm.
And one of the things that Joseph and I have been talking about is maybe finding a way through Trout Unlimited to help put in some more woody debris
Mhm.
in the river, you know, downing some trees and having the some part of the tree stay in the river. And certainly there's rivers that have a lot more woody debris than
Yep.
the east branch does. Is that something you think would help, or what are your thoughts on that?
So if we kind of follow, you know, maybe, you know, a hypothetical argument that says, you know, trout have fewer invertebrate forage base, and so, you know, they're turning to, you know, piscivory to feeding on, you know, small fishes, whether they're dace or shiners or young trout, to meet you know, to meet their needs. And if there's a dearth of woody debris, you know, those younger size classes of fish and young trout, you know, have less of, you know, less, you know, refuge places to escape that predation. So, certainly adding woody debris would, you know, improve the amount of area that younger fish and younger trout could escape, you know, predation effects, whether that's, I mean, for woody debris, I mean, even the, yeah, whether that's, you know, a 20-inch trout trying to eat them or a kingfisher. So, yeah, there's a PhD student here, maybe 10 years ago that did a bunch of work on improving habitat and woody debris and in streams. And, you know, you definitely, there's, you know, there is, you know, a clear benefit to that as far as, you know, adding, they call it habitat complexity. You know, I mean, if you look at like the screen behind Glenn there, you know, it's that riverscape, you know, I mean, that's pretty homogeneous, right? I mean, you know, a point, you know, kind of lower left and upper right is pretty, you know, what's the benefit of being here or there? You know, if there were, you know, a treetop down there, then, you know, you could see how, you know, just by adding habitat complexity, you're going to improve, you know, at least from a, you know, predation standpoint anyway, yeah, you know, improve young year survivorship.
Yeah, I think, Glenn, this might be another, and Joe, you guys on the East Branch, if you're looking, you know, this might be another tool, right, to select for Tracy and Molly and others to be selecting restoration opportunities, right?
Yeah,
Because-
I already made contact with the local beaver club,
Mhm.
and I have it in there with the guy with the head beaver there. So I think we can bypass a lot of these regulations. They just need a few treats and some good locations, and they'll do
Good.
the work, you know, under the radar.
They don't
Much-
need permits. They don't need permits either.
No permits.
Much,
All right.
much,
yeah.
So I will
much
say
better
maybe
than
the
raising the
final
water
thing
temperature.
about woody debris. So I mean, I'm around here now because I'm doing this stuff, but normally I go out to my house in California in upstream in Santa Cruz County, and I live on a tributary of the San Lorenzo, which is the river basin that drains the north slope of Monterey Bay, and you know, the floods that we had, was it 2 summers or 2 winters ago, or last one? I guess it was last winter. And you know, obviously there you have, 6-foot diameter redwoods that are falling into the streams, and so there's an enormous pulse of woody debris that went into that system, in January and December and of last year. And when I walked around some of the spots like in March before I came, or April before I came back, so you get wild steelhead runs from the Pacific and coho. I think it's the lowest, one of the southernmost coho streams on the coast. It was just like a brand new stream. I mean, you had all sorts of pockets and stuff for like the, getting the steelhead, the par to refuge in, and woody debris will often create kind of some scour pools, which will, deepen the areas and add more refuge and some lower water refuge in the case out there. So, it's definitely a benefit. I know historically people, however you want to define that, managers or DOT or would be like, oh, we got to clean up the stream. This looks awful. But like, you're actually doing a huge disservice, when you're doing that. So, all right.
Well, I'm sure scientifically you'll find that woody debris is much better than warming the water.
I like that, Walter.
All right, we're gonna end it. We're gonna end it. Thank you, everybody. Thanks for hanging in, everybody. Jeremy, thank you again.
Yeah.
Thanks again, Jerry.
Yeah, hey, I got a quick
Hey, guys.
couple comments. I know I've been sitting back watching everybody. Can everybody hear me all right?
Yeah.
Jeremy, wonderful what you've done with your study so far. The questions that have to do with habitat and the habitat of bugs themselves, and just to bring to light, the cold water that Glenn and we all know about affects how the Titymo growth in those upper reaches like Stylesville and Downsville, and that Titymo covers the available habitat for the other macroinvertebrates, i.e. different species of mayflies, because the niche is there because so those particular things all tie into that temperature component that we're talking about. Walter, I don't think we're going to be able to warm the water, but it would potentially have, I guess the question I have, is there any correlation that you could, or any study that you could equate to the vegetative or the Didymo growth versus one area versus another area, and the impact that has on the diversity of the macroinvertebrates? In other words, if the Didymo's there, the midges got a place to live, but the mayflies don't.
Right. So there's one figure that actually I think I don't know by the time I pull it up. So and it's a kind of a coarse metric. So at each of these sites, I'm collecting, a net full of organisms over a relatively consistent area, picking these subsamples out. And so with that gridded pan, I know what proportion of the sample that I've, picked through to achieve like a certain, 100 organisms or 200 organisms. So from that, I can then estimate the total abundance per sample. Does that make sense? So what we're seeing, what I did see is that you actually have more organisms per sample in these, I'll call them heavily, it's not vegetation, but heavily vegetated, we'll call it, locations upstream, Downsville and Stylesville and Deposit, where you have that heavy algae cover. But that was before I did the actual community assessment. And so initially that kind of is a bit intuitive, because you're like, well, you have this growth, you kind of have, three-dimensional habitat that things can colonize. So you would expect more than just say a flat river bottom. But once we got the the actual community data, that multicolored, panel, you're seeing you have a lot more organisms, but they're not, they're midges, they're flies, they're isopods. So, you might get, 3 times the amount of organisms per sample, say at Stylesville, but you're not getting mayflies and caddisflies, you're getting midges and scuds and aquatic worms. So even though you're getting more organisms, you're not getting, what I think we'd all consider preferred organisms. And part of that, I think, is, even though you have, the hard substrate, is consistent, like exactly as you indicate, as the Didymo, as other algae fills in those, interstitial spaces, those gaps between the stone particles that all the invertebrates go in to reside and feed. It's kind of a form of, de facto habitat limitation, even though the actual, we'll say, baseline habitat is actually adequate. So exactly to your point, I haven't, when I took the substrate assessment, I did record whether when I encountered a particle, was it algae covered or not. So I can analyze, is there a correlation or a negative correlation rather between, algal density and in particular invertebrate abundance. So I have actually had that capacity as well. And it was something I was gonna eventually look at here, kind of, the next 6 months. Yeah, I can say at least casually that there seems to be an effect of that, a negative effect of that in terms of how you see these invertebrate communities assemble. A caveat would be how much of is there, what's the confounding effect of the temperature? Because the temperature would kind of have, I'd say, expanding relationships where, the cooler water, the higher phosphorus is improving, your capacity for the algae and Didymo, but it's also depressing the invertebrates. So you're kind of going like that, kind of with those two factors. But I will say that
I'm just going to throw something out there that just came to mind with a parameter potentially.
Yeah.
That habitat assessment value that you might be able to, whatever that particular 100 centimeter or 100 square inches that you're dealing with, that you actually do a habitat assessment value for the macroinvertebrates. What's really there? If you're going down and doing that random sampling with your finger blind test down to see what the substrate looks like, you should also be able to do some kind of associative collection to evaluate whether that substrate is occupied or what its available habitat is.
Yeah.
For instance, like the extreme value being that it's completely covered with Didymo, the other value being that it's completely barren.
Oh, I see what you mean. Yeah, I see what you mean.
So you could put actually an assessment value onto the substrate as a corrective factor.
Yeah.
Does that make sense?
Yeah.
All right, hey folks, for my 4th try to end this call, I'm going to succeed. Ben, if you have additional, that's okay. If you have additional stuff, we can always arrange conversation, or you can, you can contact Jeremy. I want to let everybody go here. It's been a long call. So thanks again, Jeremy. And everybody, thank you. We'll talk again in January.
Okay.
Thanks for coordinating this. Take care.
Yep.
Bye.
Thank you.